So I guess we can start. So welcome all to the afternoon session of today's talk. And the first speaker is Gergely Harcos from Alfred Rainy Institute of Mathematics, Hungary. And he's going to talk on beyond the spherical Sup-norm problem. Thank you.
Thank you for the introduction and thank you for the invitation. I'm happy to be here, if at least virtually. I would love to be there in person, but the higher powers didn't want it to happen. So the title of my talk is Beyond the Spherical Sup-norm problem. So in the beginning, I'd like to motivate the Sup-norm problem a little bit and explain what spherical means in the title. And then I will talk about non-spherical stuff so that we can finally understand what the problem is, what the problem should be, and then I will state my new results and sketch some of the arguments, some of the ideas that go into the theorem. So it's always good to start a lecture by pictures. So here are some pictures just for fun about Maass forms on the modular surface. So the modular surface is the upper half plane, so hyperbolic plane, divided by the discrete action of SL2Z on it. And here is a little gallery of plots of these Maass forms when restricted to the fundamental domain. In fact, the fundamental domain doesn't fit on this page. So here you see a compact part of the fundamental domain. The modular surface is not compact. And these pictures were created by Fredrik Strömberg, and they were taken from the L function and modular forms database. I'm not sure if these pictures are available anymore. So here are some custom-made pictures by Fredrik for me. Actually, if you read the title of each slide, these pictures, one even and one odd mass cusp form with Laplace eigenvalue about 10 to the 3. And here is a pair, an odd one and an even mass form of Laplace eigenvalue about 10 to the 4. And here is a pair of pictures for mass forms with Laplace eigenvalue about 10 to the 5. In fact, I can even show you big versions of these pictures. So here is how these mass forms look in the large without restricting them to the fundamental domain. So very beautiful wave functions with the arithmetic symmetries coming from SL2. Some symmetries are obviously visible in the picture, some more subtle symmetries provided by the Hecke operators, which are p-adic analogs of the Laplace operator, one for each prime. They are less visible to the eye, but they are there as well. So here is one Laplace eigenfunction on the modular surface with a larger Laplace eigenvalue. Again, very beautiful ornamentic picture. And here is one with an even bigger Laplace eigenvalue. Okay, so I go back to my slides. So we are number theorists. So for us, it's clear why we cherish these mass forms. But interestingly, there is an intricate connection with mathematical physics, and in fact, the Sup-norm problem in the large as an industry came to be with a seminal paper by Ivanets and Sarnak in 95, around the time when Sarnak was exploring developing his ideas about quantum chaos. So the Sup-norm problem can also be motivated from the point of view of quantum chaos, that is from the point of view of mathematical physics. And it's just amazing that deep behind the fundamental laws of nature seem to be the same kind of wave functions as behind the fundamental laws of arithmetic. So the common language being language of symmetry. So I thought to connect my talk a little bit to the very nice talks by Rizwan and Bingrong by just quickly saying a few words about what quantum chaos is about and how the Sup-norm problem is connected to quantum chaos. So quantum chaos can be understood within quantum mechanics, more precisely via understanding the interplay between classical mechanics and quantum mechanics. And for my very short introduction, let M be a compact orientable Riemannian manifold. And let's consider a particle that moves freely on M with unit speed. So this dynamical system has a classical description and the quantum description as well. And here in this little table, you can see the dictionary. In classical physics, the particle's position and momentum or velocity are encoded as a point on the sphere bundle or unit sphere bundle or unit tangent bundle of the manifold. I want to emphasize sphere bundle and the notation SM because sphere here is the same kind of sphere that figures in the title of my talk beyond the spherical Sup-norm problem. So sphere in the title is the same kind of sphere as here. And so moving particle, moving as a function of time, is encoded into a function from the real line standing for the time axis into phase space. And we think of this function as being smooth, bounded observable, and phase space for this introduction is a smooth real valued function on phase space. And then on phase space, there is an action of a one parameter group, the geodesic flow. And of course, not only points in phase space can be flown by this flow, but also bounded observables or moving particles for that matter, composing for a by the geodesic flow from the correct side. And in quantum mechanics, the role of phase space is played by a Hilbert space L2M. So interestingly, both position and momentum are encoded in those functions, those wave functions in this Hilbert space. And then a moving particle becomes a moving wave. So a wave function, a function in L2M depending on or L2 normalized. And then bounded observables become self-adjoint and bounded operators on this Hilbert space, and the geodesic flow becomes a flow on this L2 space, which is given explicitly as e to the minus it square root of the Laplace operator. The Laplace operator corresponds to the Hamiltonian of the system that I didn't display here. It's also called the quantum Hamiltonian. So the relevance of this quantum flow UT becomes apparent when we look at solutions of the Schrödinger equation. So the Schrödinger equation describes how these waves move. So if we choose a Laplace eigenbasis phi j of the L2 space M, then to each phi j there corresponds a standing wave, a wave function that depends on time, but when you look at its size, its absolute value, it doesn't change in time. So these are simple-minded solutions, e to the minus it square root lambda j phi j of the Schrödinger equation. And then if you compose such standing waves, which are secretly moving, but you don't see this movement, you don't observe this movement, then a linear combination sum of Cj of these times these standing waves where Cj is in L2n, so square integral sequence. That linear combination will, of course, change in time in an observable way, even when you put an absolute value. So you start from an initial moment, say moment 0, wave size 0 in L2m. You decompose it as sum of Cj, phi j in this Laplace eigenbasis, and then you let it flow by this quantum flow ut, and then you get this wave that is changing in time. Now, an important, very important theorem in quantum chaos is the quantum ergodicity theorem of Schnirelmann, Polinda-Verdier, and Zeldich, which says that if the classical system that we are considering, that is the geodesic flow on classical phase space Sm, which is the sphere bundle of M, is ergodic, and as before, we consider a Laplace eigenbasis, an orthonormal basis of L2m phi j with Laplace eigenvalues lambda j. Then, if we choose a positive quantization, then the linear functionals OP phi j, so this inner product OP phi j as a linear functional on the set of classical observables A. So A for us is a smooth function of Sm, can be expressed as integration against a Borel measure d omega j that is called in the theory the Wigner measures. And then the theorem says that these Wigner measures, at least along a subsequence of lambda j of density 1, tend in the weak star topology to the Liouville measure. So the Liouville measure is the most natural measure that you can put on Sm. It comes from the volume form on the Riemannian manifold. Yes, Ian?
I'm sorry to interrupt. Could you remind us what the definition of op A is?
Well, that's a complicated thing.
Okay, maybe
so
not.
I cannot. And there are many ways to make an OP out of A. This is called quantization, and there are many how to say conventions. So it's not a unique. To some extent, it's an intuitive process. So there are many versions, and I won't be able to recall. It's just yeah. So nevertheless, even without having defined OP for you, I can kind of sketch a proof of this theorem. So with the proper notation, setup, and ideas and background, the proof is not that bad. I will only spend a minute on the proof because this talk is not about quantum chaos. But the point is that without loss of generality, we can assume that A already has a space average 0. So it suffices to show this limit property for functions whose integral is 0, because you can always subtract the constant and get the integral 0. And then the idea is to take a large capital T and average A by the geodesic flow over the interval 0 capital T. And then in a few steps, in a few clever steps using Yegorov's theorem that, again, I don't have time to recall, but basically in our situation, it says that the average of this quantity that you want to show to be small doesn't change much when you replace the symbol A by this time averaged symbol A capital T. And then, so Yegorov is the first equation. Then a simple-minded upper bound by Cauchy-Schwarz. Of course, here we use that we are dealing with measures d omega j. And then this average turns out to be a very close the measure with respect to Liouville measure as a result of the local Weil law, which generalizes the usual Weil law for the eigenvalues. So the usual value would be an asymptotic formula for sum of lambda j up to lambda of 1, which I abbreviated by n lambda 1 in this slide. And you can average such integrals as well. And so the ratio of the two averages tends to the integral of AT capital squared against the Liouville measure. And then we apply the Birkhoff-Ergodic theorem to show that this integral is less than epsilon if capital T is sufficiently large. So in the end, what one sees is that if lambda is sufficiently large, then the left-hand side is less than epsilon. By the way, the local Weil law implies that the d omega j's tend to d omega in the Cesaro sense, and now we see a strengthening of it, that if the geodesic flow on phase space is ergodic, then not only in the Cesaro sense, but in an almost sense, d omega j's, these Wigner measures tend to the Liouville measure. And here I should add perhaps that if this classical observable A only depends on position, so it is independent of the tangent vector attached at that point, then in fact this d omega j is nothing but phi j absolute square times d omega. So in particular, these phi j absolute square densities tend to the uniform distribution along almost all lambda j's. So ergodicity is reflected in this quantum ergodicity property, and then quantum unique ergodicity is the phenomenon which holds in certain special cases and is expected to hold in many cases, that there is no exceptional subsequence of lambda j's along which this limit property doesn't hold. So in fact, the d omega j's in many situations should tend to d omega in the weak star measure. And arithmetic quantum chaos looks at this phenomena in an arithmetic setting when M is an arithmetic manifold, and in that case the phi j's can be assumed to be Hecke eigenfunctions as well. In fact, in the situation important, relevant, very relevant for us in this talk, when M is the modular surface, and now for a moment, let's forget that M, the modular surface, is not compact. Let's pretend it is compact so that the previous theorem would apply to it. Anyways, the geodesic flow on the sphere bundle, on the unit tangent bundle, which can be identified with SL2R mod SL2Z, is ergodic. And this is a theorem of Hopp from 1936. And again, the proof is very simple, in fact, simpler than the previous proof, so that a sketch of it fits on one slide. And here is how it goes. So let's take an L2 function on SL2R mod SL2Z. Let's assume it is fixed by the action of the geodesic flow, that is by the right action of positive diagonal matrices, AA inverse. Then what one can observe is that, in fact, as a consequence of some matrix arithmetic magic, upper triangular matrices 1B1 also fix F. And the reason is that here both instances of F can be replaced by AA inverse F. This second AA inverse can be brought to the first term after inverting. So in effect, 1B1 has been replaced by a conjugate of it by AA inverse. And if you evaluate this conjugate, the effect is that B has been replaced by A inverse B, and if A tends to infinity, then this A inverse B just diminishes. So this in the third line, this matrix just tends to the identity matrix, and so the left-hand side tends to 0 in the end. So upper triangular matrices, because already we are assuming that diagonal matrices or fixing F and then 1B, 0, 1 unipotent upper triangular matrices also fix F. So altogether, any upper triangular matrix fixes F, and similarly, any lower triangular matrix fixes F. In the end, the entire group fixes F, and then it's easy to see that F is constant almost everywhere. So it is safe to say that on the modular surface, the quantum ergodicity conclusion holds true. In particular, almost all the phi j's, these classical Laplace eigenfunctions, also called Maass forms for the modular surface, or equidistributed. And then in a major breakthrough in 2006, Lindenstrauss, with a supplement by Sundararajan in 2010, proved that if the phi j's are furthermore assumed to be Hecke eigenfunctions, then in fact the phi j's are equidistributed no matter what. So quantum unique ergodicity for Laplace Hecke eigenfunctions, also called Hecke Maass forms, holds true on the modular surface, which first is surprising because the geodesic flow, so classically the geodesic flow on the modular surface is not uniquely ergodic. There are many ergodic measures on the modular surface. There are, for example, closed geodesics. But the quantum unique ergodicity theorem says that these special orbits are not reflected at the quantum level. So you, in the long run, if J is very large, you will not see any scoring, for example, along closed geodesics. So Sarnak was exploring these ideas, formulating conjectures, proving theorems. In the mid-90s, when he, as a problem that connects well, he started to explore the supremum norm of these Hecke Maass forms. So that brings us to the spherical Sup-norm problem, and I will explain in a second why the term spherical. So here is the famous celebrated theorem by Ivanets and Sarnak from '95, which says, so let me suppress the index J, let me just say that let phi be an L2 normalized Hecke Maass form on the modular surface of Laplace eigenvalue lambda. So L2 normalized means that the L2 norm is 1, so the average size of the form is 1 in the L2 sense. Then the supremum of the form, denoted by phi infinity, is cannot be much bigger than lambda to the 5/24. So that's the theorem. And amazingly, this 5/24 hasn't been improved since. So in a sense, 1/4 is the trivial exponent, which corresponds in a sense, or is the analog of the convexity bound in the L function setting. And of course, these Sup-norm problems are very relevant when working on subconvexity problems. So the two fields, subconvexity and Sup-norm business, are quite connected. So maybe the initial goal of Ivanets and Sarnak was to show that for Hecke Maass eigenforms, the exponent 1/4 can be improved, and they did improve it to 5/24, but it seems they were calculating very precisely. They were very much to the point. They were very sharp in that until now, their exponent couldn't be improved. Now, in the earlier slides, we saw from the physics point of view how it was very relevant to pass from the modular surface to this covering space SL2 or mod SL2Z. And the effect is that the upper half plane was replaced by SL2R, which is a group. So there is a natural group action on this quotient on the right by SL2R, which is a big advantage. So here as well, we can make such a lift, and we can start to think in terms of SL2R mod SL2Z rather than H2 mod SL2Z. Namely, H2, the upper half plane, can be understood as a quotient of SL2R mod SO2R. So this is very familiar to most of you, or maybe even all of you. And then the functions phi in this theorem can be thought as functions on a double quotient SL2R mod SL2Z over SO2R. And these functions therefore span a certain subspace of the cuspidal subspace, namely the subspace fixed by the right action of SO2R. And here I introduce an important terminology that is very widespread in the subject. They span the so-called spherical subspace of the cuspidal subspace. So here, spherical is the adjective in my title, beyond the spherical sup-norm problem. So here I'm discussing the spherical sup-norm problem because we are looking at the sup-norm of spherical Hecke-Maass cusp forms, namely those that are SO2 or invariant. Now, in adelic language, at least when phi is an even Hecke-Maass cusp form, that is, phi is fixed by the special Hecke operator t-1, these functions can be lifted to the Adel group PGL2AQ so that the lifted form is invariant on the left by PGL2Q and invariant on the right of PO2R times the product over the prime numbers PGL2ZP. So here on the right-hand side, you see a compact subgroup of PGL2AQ, which is a product of maximal compact subgroups, one for each place of Q. So PO2R is a maximal compact subgroup of PGL2R, and then for each prime P, PGL2ZP is a maximal compact subgroup of PGL2QP. So at least for PGL2, we would say that the functions phi, at least the even ones, are spherical for PGL2 at every place of Q. So there is a slight mismatch about being spherical at infinity for SL2R and PGL2R. So maybe you want to assume that the forms are even for this token, then this little difference disappears. Now, well, if you look at the adelic version of the theorem, then you can see that it's natural to replace Q by a number field, and in fact, the above theorem by Ivanets and Sarnak has been generalized to number fields by myself and my collaborators. But for this talk, I will only recall a special case for the Gaussian number field Qi that we proved earlier. So this is a joint result with Valentin Blomer and Georgia Milicevic that we proved in 2016, and the general version for arbitrary number fields also included Peter Maga as a co-author. So let me just emphasize the generalization to the Gaussian number field Qi. In this case, the associated arithmetic manifold is a three-dimensional hyperbolic, so it's a hyperbolic threefold, hyperbolic three space divided by SL2Zi, Zi being the ring of Gaussian integers. And the theorem is same as before, except that the analog of the exponent 5 over 24 there is now 5 over 12. And again, this theorem, which is an exact analog of the Ivanets-Sarnak theorem, is about spherical Hecke-Maass forms. And let me not read every line in detail. Just parallel to the previous slide, we can see that this theorem is really exploring SU2C invariant Hecke-Maass forms on the group SL2C. So there are two important differences. Once you switch from Q to Qi, SL2R becomes SL2C, SL2Z becomes SL2ZI, and SO2R becomes SU2C. And here again, we can distinguish between even and odd Maass forms. The role of T-1 is played by Ti, the special Hecke operator at I, which is an involution. And in case the eigenvalue of Ti, eigenvalue of phi for Ti is +1 rather than -1, then the form can be understood as an idyllic cusp form for PGL2 over this number field Qi that is spherical at every place of Qi. So here, instead of prime numbers, P runs through the prime ideals of the ring of Gaussian integers. But for most of the talk, what is relevant is what's happening at the Archimedean place. But as we also rely heavily on Hecke operators, I thought of giving you the idyllic picture as well. And in fact, if we let gamma GK to be a triple of groups, any of the triples in this table, so these were featured on the previous slides, so SL2Z, SL2R, SO2R, or SL2ZI, SL2C, SU2C, or their idyllic variants, then it turns out that the previously featured cusp forms phi can be understood very well from a representation theoretic point of view. So, in fact, we have very nice and very canonical Hilbert space decompositions of various L2 spaces into irreducible G spaces, and they're spherical, that is K-invariant subspaces. So if you look at G mod gamma, which for example can be SL2R mod SL2Z, a modular surface, the unit tangent bundle of the modular surface, or SL2C over SL2ZI, which is a unit sphere bundle of this modular threefold, then this cuspidal space decomposes discretely as an infinite countable direct sum, Hilbert space direct sum of irreducible G spaces. The pi's that occur here are called cuspidal automorphic representations for the group G or the pair G and gamma. And if you look at the K-invariant subspace of the cuspidal subspace, which in effect is the same as modding out the space by K on the right, then of course in this decomposition you replace each space, irreducible G space V pi by its spherical subspace, K-invariant subspace V pi K. Of course, you only need those pi's in the second decomposition for which the K-invariant subspace is non-zero. So those are the representations pi that are spherical. So with respect to K. Now, here already we see an advantage of featuring the idyllic groups, because if we switch to idyllic language and say, for sake of simplicity, we only deal with even forms as explained before, then this decomposition is absolutely unique. So you have no choice. You cannot vary pi in any sense. This is formulated as the multiplicity 1 theorem or a corollary of the multiplicity 1 theorem. And in this case, so when you use the idyllic language and irreducible G space is meant with respect to the action of the full idyllic group, the spaces automatically consist of Hecke eigenforms. At any rate, the non-zero subspaces that figure here are always one-dimensional, and they are of the form C5, where phi is a spherical Hecke mass form as before. So now we have a good understanding from a representation theoretic point of view, or at least from the point of view of this Hilbert space decomposition, where the phis come from. They span the one-dimensional K-invariant subspaces of those irreducible G-space constituents for which the K-invariant subspace is non-zero. Now, at this point, it is natural to raise the question, how can we estimate, what can we say about the non-spherical forms? So if we pick forms from V pi that do not lie in V pi K, then how can we estimate those? And for this, to answer this question and to ask the right questions, it is worthwhile to look at the unitary dual of SL2R. And just very quick, because it seems I'm getting short on time. For SL2R, there are four kinds of families of cuspidal automorphic representations: spherical and non-spherical principal series, holomorphic and anti-holomorphic discrete series. And these four types can be clearly distinguished by looking at how they decompose into irreducible K spaces. So K in this case is a commutative Lie group SO2R. So the irreducible K spaces are one-dimensional, and then you can see that, well, you can parameterize the unitary dual of K by integers. And then for the spherical principal series, we get irreducible K spaces corresponding to the even integers. These are one-dimensional bits, which together make up the whole space, VIT plus, so plus stands here for spherical. In the non-spherical principal series, there are no K-invariant vectors, so the K characters that occur correspond to the odd integers. And then there are also the holomorphic and anti-holomorphic discrete series. For the holomorphic ones, again, these are one-dimensional bits, but the L's now have a minimum K, and all the L's are congruent to K mod 2 that occur. And for the anti-holomorphic discrete series, there is a maximal L, which in that case is a negative integer. So K is always a positive integer in this classification. So each of the V pi's in the case of G equals SL2R or PGL2AK can be classified into one of these four types. And then say you can pick your favorite vector from each of these one-dimensional bits. So earlier we looked at the L equals 0 piece that only occurs in VIT plus. Anyways, inspired by the theory of new forms in the level aspect, the natural non-spherical Sup-norm problem would concern a minimal weight vector in the holomorphic discrete series, or a maximal weight vector in the anti-holomorphic discrete series. However, there is a catch. So such a vector automatically has a large Laplacian eigenvalue. So the weight aspect in the situation of SL2R is not really separated from the eigenvalue aspect. So to go genuinely beyond the spherical Sup-norm problem, I argue at least we are led to work with SL2C rather than SL2R. But in fact, for SL2R, there are results about non-spherical vectors. For example, there is a nice result of Shia for about bounding holomorphic Hecke-cusp forms, and for co-compact discrete subgroups gamma, there is a similar result by Kayutin-Steiner, which improves an earlier result by Shaumo Das and Jyoti Sengupta. So Shaumo is an organizer of this conference, and Jyoti is an active participant in this conference. He was asking many questions already. So let's switch to SL2C. I think I explained why SL2C is better for a good non-spherical Sup-norm problem. In this case, the unitary dual was, so the unitary dual always means classes of irreducible unitary representations, unitary meant on Hilbert spaces. And in fact, the unitary dual of SL2C was determined earlier than that of SL2R, namely by Gelf and Naimark in 1947. Beautiful 100-page long paper. And in this case, the relevant ones, so in fact, for SL2R, I only consider the tempered ones. Those are the only ones that occur in our situation of the modular surface. And for SL2C mod SL2ZI, again, only the tempered ones occur, and they come in a single family, PITP. So in this case, the unitary dual is parameterized by two independent parameters, T, which is a non-negative real number, and P, which is a half an integer. And just as with SL2R, these representations can be defined very explicitly. In the case of SL2R, by various actions of G on L2R, and in this case on actions on L2C. But there are many models for these irreducible unitary representations. And now it is instructive and in fact crucial for us to look at how these representations decompose into irreducible K-spaces. So VITP decomposes into irreducible K-spaces, and note that K in this case is SU2C, it's no longer commutative. So not all the irreducible representations are one-dimensional. In fact, for every non-negative integer, there is a unique irreducible representation of SU2C with that dimension. At that dimension, I will denote by 2L plus 1. So for VITP, there is, let's assume that P is non-negative, then there is a 2P plus 1 dimensional piece, and then a 2P plus 3 dimensional piece, a 2P plus 5 dimensional piece, and so on. And each of these higher dimensional K-spaces can be naturally decomposed into one-dimensional subspaces if we refine the picture by the action of the diagonal subgroup of SU2C, which is commutative. So the basis that you obtain of each of these 2L plus one dimensional spaces, VITPL, is called the Wigner basis, and the one-dimensional spaces spanned by them I denote by VLQITP. So this is how the structure of a pi occurring in the earlier considered spectral decomposition looks like. So each pi for the case of G SL2C can be understood as PITP for some T and P, and this is how the K-space decomposition looks like, and this is how the K-space can be further decomposed into one-dimensional subspaces. So after this preparation, I can finally state the new result. So the point is that the P parameter, which measures the lowest K-type in the representation, so 2P plus 1 is the lowest irreducible dimension of the lowest dimension of an irreducible K-space contained in the space of PITP, is quite independent. Well, it is independent of the T parameter, so that gives rise to a natural question and the natural theorem. So the theorem is this. So let's assume that we are looking at the cuspidal representation. It's an irreducible G space in the cuspidal subspace, whose parameters are T and P, and T I think of as being bounded, and P I think of as being plus minus L, where L is our main parameter. L is a positive integer. So I'm looking at pi's whose T parameter is bounded and whose lowest K type is L, or the lowest dimension of an irreducible K space in it is 2L plus 1. And then we take this Wigner basis phi q. So phi q, each phi q is an eigenfunction of the diagonal subgroup of K with the relevant character. So phi q spans the one-dimensional space V pi L q, and then so the benchmark bound, as we learn later, if we get to it, for the sum of squares of phi q g's, also G is constrained in this theorem to a compact subset, so G is also bounded. So we are interested in bounding the total size of these phi q's. The benchmark or easy bound would be L cubed, as we'll see later, and we can improve this to L to 8/3. And for individual summands, the benchmark bound would be L, and we can prove a non-trivial improvement of it. So the exponent we could decrease from 1 to 26/27. And in the case when Q is special, note that Q runs from minus L to L. So if Q is in the middle, Q is 0, then we can interestingly improve 26/27 to 7/8 by specialized techniques. And when Q is on the side, plus minus L, then we can improve the exponent to 1/2. Now, I only have 15 minutes left, so I would like to sketch the proof, or at least some of the ideas that go into the proof. So following Zellberg's seminal work from 1956, we consider an integral operator given by convolution on the right, essentially. So we look at an L1 function on the group G, and we look at how this function acts on the whole L2 space, G mod gamma. So this gives rise to the automorphic kernel that is in this big parenthesis. And let's assume that this operator RF, which is really just a convolution operator, is positive in the sense of function analysis. And let's assume that this positive operator acts by the scalar CPL on the irreducible space V pi L that we want to, that we are focusing on. So RF when restricted to V pi L, or RF when restricted to V pi acts by pi f, and let's assume that this pi f acts by a scalar C pi L, non-negative scalar on V pi L. Then, well, positive operators are self-adjoint, so RF preserves the orthogonal decomposition, V pi L and its orthogonal orthocomplement. And in fact, you can check easily that RF composed with the projection to V pi L can also be described in terms of a kernel, just like RF, except that instead of this sum over gamma, we have this expression. And you can check that with this kernel, this is a reproducing kernel, you do get back RF composed with the projection V pi L. So we are looking at two positive operators, the whole RF and its restriction kind of on V pi L. So RF composed with the projection. And as happens with positive operators, then RF majorizes this composed variant, composed with the projection. And then by a simple approximation argument, this inequality, RF being at least as large as the projected version, propagates to an inequality between the kernels and the diagonal. So if you look at the two kernels, the first kernel and the second kernel, and you put G equals H, so you look at them at the diagonal, it turns out that the first kernel majorizes the second kernel. So this is the basic method of estimating this sum that we are interested in. And then this technique can be refined to look at the individual pieces. In fact, this picture, because we are looking at G equals SL2C, doesn't involve Hecke operators, but you can tell the same story adelically. And that's another reason why I told you to look at the adelic versions as well. So if you work adelically, then not only this decomposition is more canonical and furnishes Hecke eigenforms automatically, but in fact, you have more integral operators to deal with. So then F is a L1 function on the adelic version of the group, and not only at the Archimedean place, but also at the non-Archimedean places, so at primes or prime, in this case, prime ideas, you can introduce this convolution operator. And still the conclusion holds true. And in fact, the famous amplification method that was explored in the Ivanets-Sarnak paper can be explained in this language as choosing on the adelic group a suitable test function F that produces a good positive operator. So you see, the idea is to make this constant C pi L large and at the same time keep the right-hand side small. And if you do this adelically, then in fact, so the Ivanets-Sarnak amplifier can be understood as a good test function on the adelic group. But here, at this point, I'm not looking at Hecke operators. I'm just looking at what's happening at the Archimedean place. Anyways, so how can we find a good test function? How can we come up with this constant C pi L? And how can we make the operator positive? So to make this work in practice, we consider all functions that act on every component VITPL by a scalar and by 0 on all the other components. So we are looking at test functions which really focus on the Lth k-type within each V pi, including our favorite V pi. And we look at all these functions. These functions form a closed Hilbert subspace, which can be defined intrinsically. And if F is an L1 function as above and also of special kind lying in this Hilbert subspace, the scalar can be calculated explicitly by a transform. So this transform generalizes the usual spherical transform or Zellberg transform or Harish-Chandra transform that is very familiar in the subject. And so given such an F, we can see how it acts on the various pieces V pi, and the transform includes this generalized spherical function, which again can be expressed explicitly. And it turns out, by the theory of Gelfand-Neumark, this Hilbert subspace is in fact isomorphic to the L2 space of that part of the unitary dual that contains the Lth k-type. And this isomorphism comes with a Plancherl identity. So F and its transform are related in the L2 sense. And in practice, we prescribe the values of the transform and we choose the function F with that function, with the prescribed function as being the transform by an inversion formula. So this is very similar to a Fourier inversion, it's just more complicated. So you can reconstruct F from nice transform by this inversion formula, where again, this generalized spherical transform plays a leading role. So both in the transform and the inverse transform, we see the same generalized spherical function. But of course, you cannot just prescribe F at ITP arbitrarily. You need to ensure that the resulting test function F is continuous and rapidly decaying and reasonable size. Otherwise, the previous ideas just don't go through. And for this, we need to understand the spherical trace function in some detail. And here are some surprises. Well, the first part of this slide is not surprising at all. It says that because the spherical trace function has a very reasonable integral representation, the IT parameter in it can be continued, can be deformed to an arbitrary complex number. So in fact, in this new complex variable, there is analytic continuation of the spherical trace function. And then comes the surprise. Once you continue the spherical trace function analytically, there are some plausible and some non-plausible symmetries. And non-plausible, I mean this second line. So in the case when you can, so nu is now this complex number that was originally IT, was originally on the imaginary axis. So once you continue analytically the generalized spherical trace function, and you go off the imaginary axis, and let's imagine that nu is a half integer congruent to p mod 1, so that you can play the game of switching nu and p. It turns out that in that case, switching nu and p, as long as nu and p are at most L in absolute value, leaves the spherical trace function invariant. So this is a rather unexpected symmetry, which shows that after all, this first parameter that was IT and the second parameter are not really independent as we thought. So these properties can be best explained by analytically continuing the representations pi ITP themselves to non-unitary Frechet representations. So it is not true that pi p nu is isomorphic to pi nu p, but if you look at the part of it that is relevant for the spherical trace function, those parts, the group acts in the same way, so they result in the same spherical trace function. And so this means that this transform f hat for a rapidly decaying f extends holomorphically, and it has this unexpected symmetry. So this means that you cannot choose f hat ITP in an arbitrary fashion, because once you continue IT to nu, it must satisfy this symmetry. But luckily, this is the only obstruction. So we proved a Paley-Wiener type theorem that characterizes what kind of f hat corresponds to smooth and rapidly decaying functions, when rapidly decaying is meant in terms of derivatives as well. And the proof follows Wang's little-known paper and proof, which characterizes the case when those f hats that correspond to compactly supported smooth functions. So compactly supported was too restrictive for us. More precisely, the conditional f hat was too restrictive for us, and luckily, well, we only need to have rapidly decaying f, and then those f hats must satisfy minor conditions. So in the end, we used the function f hat nu p, which satisfies the symmetry and the other conditions of the theorem, so it corresponds to a good or f. And so it does produce a constant c pi L, which is at least 1 over L for our favorite pi, and an f that decays rapidly with good uniformity on L square. On the other hand, and this is not too much of a surprise, this only yields the baseline bound L cubed. And in order to improve on this, we need to amplify pi, following the ideas, following Ivanets and Czarnak in their footsteps. And here I'm very brief. I cannot explain this in any detail, but we use a standard amplifier, and the sum of phi qg squares is in the end bounded in terms of such a quantity where you see that the spherical trace function makes a key appearance. And then we prove bounds for this generalized spherical trace function. In effect, the theorem is saying that this generalized spherical trace function is concentrated at the identity. So you can see there is a trivial bound of L for the spherical trace function. And unless z is very close to 1 and u is very close to 0, you can conjugate by k every h into an upper triangular matrix, and in this upper triangular form, z must be close to 1 and u must be close to 0 to avoid large values, or unless z is very close to 1 and u is very close to 0, this function is much smaller than L. And so we analyze the various gammas in this formula, we very rarely, so in most cases, we get a much better bound than the trivial bound L, and this is how we prove our theorem. And I'm really at the end, but the theorem was also about estimating single phi q's. So for this, we compose RF with a projection operator, which analytically is achieved by looking at how we defined f in terms of the spherical trace function using the inversion formula, and the spherical trace function we replace by a Fourier coefficient along this diagonal subgroup contained in SU2C. And once we replace in the inversion formula the spherical trace function by this averaged version, we get a similar bound, but now for an individual phi qg. And again, we need good bounds for this averaged generalized spherical trace function. And this is, let me tell you, it's very complicated stuff. So these theorems, the previous one and this one, they are very non-trivial to achieve. And again, we see from this theorem when to expect. So already the L to the epsilon bound here is highly non-trivial, but we see that when Ag is somewhat away from K, the maximal compact subgroup, or D, the diagonal subgroup of SL2C, we get we get the saving, we get a much smaller bound than the trivial bound. And this is the end of my talk. I was rushing somewhat around the end, but I will share the slides with you, and then you can study the details that I missed, or you can just read the paper, which I'm afraid is rather lengthy. It's almost 70 pages, but it shows that the theorem is non-trivial. So that's the end of my talk, and thank you for attention.
So, nice, beautiful talk. Questions or comments?
Yeah, in your theorem, the implied constant in the first inequality, that is depend on the set that you're choosing. So, so how does this translate to Sup-norm when you consider non-compact quotients?
So we didn't prove anything in that case. So our analysis, so you see, in this analysis, this value of the spherical trace function and its average variant depends heavily on G, and we use crucially in our analysis that G is bounded. So I cannot tell you what this method would give for G leaving every compact subset. So for unbounded G, I'm not saying it's impossible to get something out of our method, but we made this simplifying assumption. In fact, so this Sup-norm problem business is really huge, and I couldn't really give an introduction to it. But so as you move to more complicated groups, say let's look at just PGL and R. So over R, but PGLN with N large, there is a huge difference between the global Sup-norm problem and the restricted Sup-norm problem. And already in the original Ivanets-Sarnak theorem, so motivated by the Lindelof conjecture, it would be natural to expect that epsilon is the truth. And in fact, Ivanets and Sarnak thought epsilon would be the truth, except it's easily shown to be false. So one can show that this sup-norm is always as large as lambda to 1/12, or maybe 1/12 minus epsilon, for very simple reasons, by examining the K-Bessel function that figures in the Fourier expansion of the form along horocycles. So so high in the cusp, these cusp forms are unusually large. In fact, they are unusually large around height square root lambda. And the epsilon conjecture is now only expected for the restricted subnorm problem when we restrict the form to a fixed compact subset. And when you move from SL2 to SLN, say n being at least 6 or maybe already 5, provably the global subnorm is larger than what you would call the trivial bound. For compact situations, there is a trivial bound dimension minus rank over 4 trivial exponent, and this trivial exponent is just false for PGL 6 and higher rank variants. One can prove a non-trivial subnorm bound for the restricted subnorm when we fix a compact subset and we restrict the form there. But it's just false when you let the point vary all over the group. It's a very different kind of problem. Okay. So maybe from an aesthetic point of view, the global sup-norm is most natural, but if you want to understand the fine behavior and prove sharp results, then you better so often it's necessary to restrict the forms to a fixed compact subset. So maybe it looks unnatural to you, this restriction, but from another point of view, it's quite natural.
So is there an escape of Maass at the cusp, so to speak, as the
I don't know, but that's the usual behavior. So if it doesn't happen, then it's more like an accident. So I don't know what happens in this situation, but I'm telling you that for PGL5, say PGL5R or PGL6R, there is definitely escape of Maass. There are huge values attained by the form high in the cusp, and that's a theorem. So there are lower bounds. In this situation, I don't know. So it would be nice to see. I don't know, and I don't have an intuition.
Can you give me references for that theorem, for that set for GL5?
So. So the authors you should look up are Simon Marshall and also Bromley and Marshall. So if you look at their papers with subnorm in the title, we will see that. And in fact, I have a paper with Valentin Blomer and Peter Maga where we try to prove some upper bounds for the unrestricted subnorm. So there are very strong lower bounds, bounds of the form lambda to the n cube. So if you look at PGL and R, and you look at a cusp form of Laplace eigenvalue lambda, say spherical cusp form. So on PGL and R mode PO and R. Let's look at the cusp form of Laplace eigenvalue lambda. Then Simon Marshall can prove, and maybe Templier is another author that you want to look at, a lower bound of size lambda to n cubed over 24. Lambda to n cubed over 24, and I and Valentin and Peter have explored what can we say from an upper bound perspective, and I don't remember the exact theorem we proved, but it's lambda to the constant n cubed, maybe n cubed over 16 or something like this. So we have a lower bound lambda to the n cubed over 24 and an upper bound of lambda to the n cubed over 24. over 16 for PGLN or mod PON or plus form of Laplace eigenvalue lambda. And these exponents, which scale with n cube, are much, much bigger than the trivial, sometimes called convexity bound in this situation, which I think is n times n minus 1 over 8. So it scales quadratically with n. And we can go even below that when restricting the form on a fixed compact subset.
Okay.
So the two bounds diverge very heavily for large n.
Okay, sir. One last question. Is there anything you can say about the non-cuspidal part of the spectrum?
Well, that's a good question. We haven't looked at that. So you are absolutely right. Well, in general, instead of the cuspidal space, you can look at the whole L2 space, and then there is an Eisenstein part of the spectrum as well. And people, for example, Matt Young, have looked at the Sup-norm problem for Eisenstein series, but certainly not in the situation we are looking at. So our paper tries to open a new direction in the Sup-norm problem, where you see irreducible K-types occurring in the cuspidal, irreducible cuspidal representation of large dimension, and we want to see what happens when you take a vector from a large K-type. So it's a first of its kind paper, and certainly that aspect has not been explored for Eisenstein series. For spherical and earlier variants of the Sup-norm problem, Eisenstein series have been examined, but of course you have to be careful how to state theorems and conjectures, because the Eisenstein series are not L2 normalized, and so you have to subtract certain parts to get a. Sorry.
Yeah, I mean, in the case of Eisenstein series, you have to restrict to a compact set and then do things inside that compact.
Yeah.
That is what I meant.
Yeah, sure, but you can do other things as well. You can look at the main term, and so if you look at the Fourier expansion, you can just treat the constant term separately, and the non-constant part you can estimate. And of course, there are variants of the Sup-norm problem that I haven't even touched upon. For example, what happens when you vary the group gamma, so the level aspect of the problem. So there are many aspects of this problem, and here I explored the weight aspect. But we looked at new forms in the weight aspect that generate a large K-type. So something that you don't see for SL2R. So in general, non-spherical forms haven't been explored. And in fact, as you see from this talk, the underlying theory for SL2C has been around for 80 years or 50 years, depending on how you count it. For example, there is this crucial theorem of Wang's that we somehow deformed or massaged into our Paley-Wiener type theorem. These things are not well known, although they concern the simplest type of group, SL2C beyond SL2R, and in fact, in certain senses, SL2C is simpler than SL2R. But these theorems have not been put into action so far. Or let me just say, this generalized spherical transform has been that we explored has been known for a while, and the key players in this transform, where are they? These generalized spherical functions. Very little is known about them analytically, and in fact, it was quite painful for us to derive some bounds for this object. So this is very different from the case of L equals 0. So when you look at left and right K invariant functions, the traditional spherical functions and the traditional spherical harmonics, there is a lot of knowledge about them. But for these generalized versions, already for SL2C, almost nothing concrete was known about them. And in our paper, we started developing. And there is there are more theorems in our paper. In fact, I mentioned that for Q equals 0 and for Q equals plus minus L, we have better results. And that's partly due to having different kind of behavior, different kind of estimates for special Q. So these generalized spherical trace functions, or rather their Fourier coefficients along the diagonal in SU2C, behave very differently for Q equals 0 than for Q equals plus minus L, for example. So they attain largish values close to different kinds of subsets or subvarieties. And it is possible that we have missed something, and there is a much more elegant treatment to derive bounds and much better bounds than what we have than what we have here. So our methods were pretty ad hoc, looking at the definition. Say, let's take this definition of the generalized spherical trace function, and then parameterize K by Euler angles, and just just estimate the integrals, the multi-dimensional integrals, carefully. And of course, on the way, we did gain some insight into these integrals, but it might happen that just by making a better use of where these functions are coming from, that they are not independent of each other, that together they serve one purpose. Maybe that way, much better understanding in particular estimates can be derived for them. So it's a new direction, and I think there is a lot of work to do here.
Okay, sir. Thank you.
Non-spherical, how to say, non-spherical trace functions, generalized trace functions, generalized spherical transform.
Any other questions?
Okay. Yeah. Sorry.
The Ivany-Cernak result, is there level aspect analog known?
Absolutely.
Who did that?
Yeah.
Can you give a reference?
Well, maybe you want to. So I mentioned this generalization. So this theorem is about the QI, but there is a number field generalization by the same authors and Peter Maga that appeared in 2020 in Journal of the EMS. You can look at this paper for references. So in particular, that paper includes the level aspect over all number fields. But that's not the first paper, of course, in the subject, but it kind of synthesized earlier papers. So we have a good bound for every number field, not only in terms of each Laplace eigenvalue. So here there are local Laplacian operators at every Archimedean place. And we have the 5/24 exponent at the real places and the 5/12 exponent at the imaginary places. But also we explore what happens for congruent subgroups, gamma 0 n for n square free. So a lot is known for square free levels. I told you, or even in the number field situation, we have a very good understanding, and it's quite subtle to see what kind of upper bounds and lower bounds one can prove for non-square free levels. And this is a huge industry, and there are many wonderful colleagues who have explored this topic, like Tampley, Abhishek Saha, Edgar Singh, many authors. Initially, the level aspect, non-trivial bound in the level aspect was achieved by Blomer and Holovinsky. That's an Inventionist paper. So, so why I recommend you to look at our paper from 2020 in JEMS, it's not because I want to advertise my work so much. well, sure, everyone likes to advertise their work a little bit, but that was not my main point. My main point was it's a paper that builds up on many earlier papers. It's a synthesis of earlier works, and it has good references. So you look at that paper and you get an overview of the subject, I think, if I recall. I don't know.
Thank you very much. It was a nice talk.
Thank you. Thank you.
Any other questions? No, I think Ian has a comment on chat box. So can we just open that?
Try to see. Okay.
I can just say it out loud.
Ian.
That helps everybody. I'm sorry that it was just, I wanted just to comment on some very small part of the long thing.
Can you say your comment, because not everybody is on Zoom?
Oh, sorry. The comment was just like you mentioned that a problem in treating Eisenstein series would be how to normalize them because they're not in L2 anymore. And I was just wanted to say that there's a very nice theory of norms on Eisenstein series in Michel Venkatesh, which I think would be the natural analog of L2 normalization, the L2 norm for the Eisenstein series. So that's all I want to say.
Yeah, so another subtle question is what kind of vectors, what do you call a new form? What kind of vectors you want to pick from the representation and want to estimate? And it turns out that so there is a whole new theory of Peter Humphreys and Archimedean new forms, and that has an effect on the sub-norm problem. And also in the non-Archimedean aspect, so sometimes not always the traditional new forms are the best guys to estimate, and again there is some wonderful activity, say by Ueke Hu and co-authors. So in this subject there are at least 100 relevant papers. In fact, 10 years ago I used to put up a table trying to collect the relevant results. Already that table had like 40 references, and then I had to stop it because I couldn't keep up with the activity. Maybe I tried to find this. Let me try to. This is another talk. Let me try to find this table for you. 1 second. One second. Oh, I don't have the table here. Okay, then where do I have the table? Maybe here. No, not here. Maybe. Sorry. I don't find the table. Okay, this is embarrassing. Anyways, this, for example, was a talk in 2010 that I gave in Debrecen, and I think this was about the level aspect of the problem. Anyways, if you're interested, email me and I will find these old slides with the table. Okay. Sorry,
Okay.
guys.
Okay, any other questions? No? Let's thank Gergely again for his talk.
Thank you so much, especially for the excellent questions. Thank you.